In this section, we're dealing with the buoyant force. And one way to look at it is to consider some volume of water. All right, so we got water around here, and let's just consider a volume. Imagine it's like in an imaginary sphere of some sort. So we're assuming that the water's not moving, which means that delta P for this little chunk of water is 0. So if delta P is 0, that means that the net force on that little chunk of water is also 0. So if we draw our free body diagram for this little chunk of water, we have F grav on chunk by Earth. And even though there's forces pushing in from all sides, we're just going to simplify and then just look at the upward force. F buoyancy on chunk by water. So if this thing is not moving at all, the net force has to be 0. That means that F buoyancy plus F grav is equal to 0, 0, 0. In other words, the buoyant force is equal to the negative of F grav, or just looking at their magnitudes, the magnitude of F buoyant is equal to the magnitude of F grav. So let me just drop the vector notation and go to scalar notation. So we have F buoyant is equal to mg, where this is the mass of that chunk of water. Now, if we imagine that we go ahead and we replace this chunk with something else, let's replace it with a solid ball, and we want to know, well, what is the buoyant force on this ball? Well, it's got to be equal to the buoyant force on that chunk of water, because by placing the ball there, we really haven't changed the water. We haven't changed how it's interacting with this little volume. So we have that the buoyant force is still equal to mg, but m is the mass of the water that used to be here. So if we look at a free body diagram for our solid little ball, we have F grav on ball by Earth and F buoyant on ball by water. So what really matters here is the relative size of these two forces, and that's going to tell you what happens. So when you're looking at this, you really want to look at the magnitude of the buoyant force compared to the magnitude of the gravitational force. Obviously, if F buoyant is larger than F grav, then this thing is going to end up floating. If the buoyant force is larger, this thing goes up. If you have the reverse situation, if F buoyant is less than F grav, then this thing is going to sink. And just looking at the relative magnitudes of these two forces can tell you something, because if you look at, say, this solid sphere in air, the air is exerting a buoyant force on it. So if this ball were just sitting on the table over here, the air is exerting a buoyant force on it. But if you actually compare the buoyant force to the gravitational force, here's my F grav, and my F buoyant is just this, oops, little thing right there. So it's essentially negligible. When this other buoyant force is so small compared to the gravitational force, we could just say, you know what, this guy isn't even there. That's why when we're dealing with a lot of our problems, we don't actually include the buoyant force, because most of the time that buoyant force is so incredibly small. Now, to actually calculate the buoyant force, it's going to depend on the mass of the fluid displaced. That's what this right here is. It's the mass of fluid that used to be in that space. Times g. So that's why a lot of times you can just compare the density of the two objects, because F grav is equal to rho for the object, V for the object, times G. So you notice they both have G in them, they both have the volume of the object. Really, it's just these two densities. But what you really need to keep in mind is that it's actually the two forces that we're comparing. It just turns out that because of the way these equations are structured, that is equivalent to comparing the densities. But you're better off comparing the forces, because then you can tell whether or not things are really negligible. So that's what I recommend to do. Now, I just want to give you an idea of how these forces come about. And so I have a couple of simulations. So here I have a solid ball, and I'm going to go ahead and pump in some gas atoms. And notice that the ball is floating up to the top of the screen. And you can see the mechanism pretty clearly here. What's actually happening is that the molecules are bouncing around. And if I go ahead and put some more in, what you will see is that the molecules down here tend to be a little bit more densely packed. And so there's more molecules down here pushing up than there are molecules pushing down. And so this is one way of looking at the buoyant force. This is what's actually happening on the microscopic level. It's the atoms below bouncing on it are actually pushing just a little bit harder than the atoms up above. That's one way of looking at the buoyant force. Another way of looking at things is, here I've got a couple of objects. And so notice that when we put the object in here, it changes the level of the water. And so by lifting the water up, we know that this thing has to be exerting a force on the system. So let me go ahead and show some of these forces. So here we have the gravitational force is the blue guy. The purple is the buoyant force. Now notice if I go ahead and displace even more water, that buoyant force increases. And in fact, if I go ahead and let this go, this thing's going to bob up to the surface until it gets to the point where these two forces are equal. Now with this brick, which is pretty heavy, that's just going to end up sinking down to the bottom. Now let's go with identical volumes. So now I have the same volume of wood and bricks. So notice the magnitude of this buoyant force. If I go ahead and drag the wood block underwater, you can see that those two buoyant forces are the same. So even though the objects have different weights, the fact that they're displacing the same volume of water means that they're going to have identical forces.